Hello and welcome to the Postcard Professor, where we take complex ideas and explain them in the space of a postcard. In the last video, we looked a bit at what exactly momentum and impulse meant. In this video, we're going to look at something called the conservation of momentum and tie that in with conservation of energy. So the example that we're using is a purely elastic collision. Essentially, what this means is we have two blocks or two objects which are on a collision course. And through the process of collision, no energy is lost. So we're able to use both conservation of momentum, which is true for any collision, and conservation of energy, which is true specifically for this purely elastic collision. So we're going to say that these two masses have mass A and mass B, and that they have initial velocities of, we're going to specify that this is before the collision. So this is VA1 and this is VB1. After some time, these two objects collide. And after that point, they will separate again, and they will have, again, two separate velocities. But this time their velocities are going to be VA2 and VB2. So first, let's state exactly what the conservation of momentum is. Now, the first thing to realize is that we have more than one body here. So in order to account for all of the momentum, we need to sum over all of our bodies. So I'm going to call this the sum of all of our mass times our velocities. So this is our momentum, and I'm going to call this of body I, and we're just going to sum over all of the i's. So in this case, I is equal to A and I is equal to B. And again, we're going to integrate from time 1 to time 2 of all of our forces. And you could write this sum either on the outside or on the inside, it doesn't matter. And this is going to be equal to all of our momentums at time 2. So I also need to specify that all of these momentums are at time 1, so I need an additional subscript, and these are all at time 2. So how would I write this for this specific case? First, for A1, I would say that mass of A times the velocity of A1. Then for B at state 1, this would be mass of B times the velocity of B at 1. I don't actually have any forces here. We have forces between these two objects, but we don't have any external forces. Or rather, we don't have any external forces in the direction that we're interested in. If we had some friction or just some extra force, if we're pushing on this, then we'd have to think about this impulse, but none of the forces that we have are what we call impulsive. They don't actually add any impulse to our system. So I can ignore this component completely and just write the right-hand side. Mass of A multiplied by V of A at 2 plus mass of B multiplied by V of B at 2. All right, the next thing I can do is write the conservation of energy. So we defined this specific type of collision as one where the energy was conserved. So we have the same amount of energy before and after the collision. So what that means is I can write the kinetic energy of both of these objects is equal before and after the collision. We don't have any potential energy here, or rather the potential energy doesn't change. So these are the only pieces of energy that we need to worry about. Now I can simplify this a little bit already just by getting rid of these 1/2 in front of each of these terms. So now that I've written these two equations, my goal is to come up with some relationship between the end velocities and the beginning velocities. And I'm doing this to expose something called the coefficient of restitution, or you may have heard it as elasticity. So all the steps from here on out are just targeted towards isolating that coefficient and defining it based on what we have right now. The first thing I'm going to do for both of these is to get all the A's on the left-hand side and the B's on the right-hand side. In doing so, I can take out an MA from both of these terms and an MB from both of the terms on the right-hand side. So MA, and I'm going to have this VA1 on the left-hand side, minus the VA2. And on the right-hand side, I can take out the MB. The VB2 is going to be positive, and the VB1 is going to be negative. Okay, so now I'm going to do the same thing for conservation of energy. And the only difference between these two is that the velocities are going to end up being squared. And what shows up here is something that we know how to factor. A squared minus b squared is just equal to a minus b multiplied by a plus b. So that's the relationship that I'm using to simplify this down. And I can do the same for the right-hand side. And what we see here is something that looks very similar to our conservation momentum. We get this ma multiplied by va1 minus va2, and on the right-hand side, we see mb multiplied by vb2 minus vb1. So because these two things are equal as defined by the conservation of momentum, we can actually divide both of them out. So we can just completely get rid of the conservation of momentum equation that we found in our conservation of energy. And what we're left with is that VA1 plus VA2 is going to be equal to VB1 plus VB2. Now this is about as simple as we can get it. But remember that we were looking at a relationship between the velocities at the beginning and the velocities at the end. So I'm going to isolate the beginning pieces and the end pieces. So to do that, all I need is to move this 1 over to the left-hand side and this 2 piece over to the right-hand side. So then we end up with VA1 minus VB1 is equal to VB2 minus VA2. And the last step here is to divide, and we're going to end up with the coefficient of restitution. So I'm going to divide the right-hand side by the left-hand side. What we end up with is VB2 minus VA2 divided by the left-hand side, which was VA1 minus VB1. And this is equal to 1. This term right here is what we've been calling the coefficient of restitution. And we usually just have a symbol E, which is also called the elasticity. And this value, being 1, indicates that this is fully elastic. So let's take a second to look at what this actually means. So VA1 minus VB1 is simply the relative motion of the objects before the collision. And VB2 minus VA2 is the relative motion after the collision. Now take a second to notice that both of these had better be positive or else there's not going to be a collision happening. So before the collision, if VA1 is less than VB1, then it's never going to catch up and actually hit this. If after the collision, VB2 is less than VA2, well, we're in a situation where they're going to collide again, and that really isn't something that makes sense. So both of these are going to be positive. And I made a mistake here, so I'm going to go ahead and fix that. That should be VB1. This value of E should never be greater than 1. And the lowest it can be is 0. 0 means that no matter what the relative motion is before the collision, once they hit, they stop moving relative to each other. So that means that they're stuck together. We can think of a fully inelastic collision as one where E is equal to 0. So this is inelastic, which means that the objects stick together. And in actuality, our coefficient of restitution can be anywhere in between these two. We can never have a situation where E is less than 0, because that would mean that these objects are moving through each other. VA2 is greater than VB2, so after they collide, this continues moving through the other object. It doesn't make sense. We can never have anything where the elasticity is greater than 1, because that would actually violate conservation of energy. That would mean that we have more energy after the collision than we did before the collision. And in fact, the situation where energy is conserved is only true when this elasticity is equal to exactly 1. So if anything else is true, then we do not have fully elastic and energy is not conserved. We lose some energy in the collision. In our next video, we're actually going to use this definition of elasticity to work through an example.